Hi everyone, I'm Fraser Cain. I'm the publisher of Universe Today. This is the question show. Your questions, my answers, as always, wherever you are across my channel. If a question pops in your brain, just write it down. I'll gather them up and I will answer them here. Now, I record this show every Monday at 5 p.m. Pacific time. So if you've got questions about any topic that you've seen, go ahead and write in the chat or join us for that live show. And then we can do follow-up questions and it's a chat where people are talking with each other. So definitely check that out. And the live show runs for about 3 times as long as the recorded version. So if you want more content, that's the way to go. All right, let's get into the questions. Dimitar Savov. Hey Fraser, love your content. Is New Horizons going to become something like the new Voyager, sending us information from interstellar space for decades to come? Also, any recent update on its activities? New Horizons is the spacecraft that was sent to visit Pluto and Charon. It took 10 years from when it launched to when it was able to finally arrive at Pluto and give us the first images of Pluto up close. It really filled in the last big unknown in the solar system, which is, what does Pluto look like? At one time, the 9th planet, no longer the 9th planet according to the IU, but don't tell Alan Stern, principal investigator. It's still a planet in his heart. After that, it kept going and it was able to do another flyby of a Kuiper Belt object called Arrokoth. And at that point, it has no other targets currently lined up, but it's still fully functional. Like the Voyagers, it's equipped with a RTG, a chunk of plutonium that is breaking down and giving out a lot of heat, and it's going to last for decades and provide the spacecraft with enough power to communicate home. It just needs another target. The problem is that it doesn't necessarily have enough propellant on board for it to make a really gigantic change in its trajectory. It has this cone in front of it that are all the possible trajectories that it can take to be able to arrive at some other destination. And the Hubble Space Telescope has been looking for new targets. Other ground-based observatories have been looking for targets. But the one that's really going to help out is the Vera Rubin Observatory, which still doesn't come online for another year or so. And that's, of course, this giant telescope that is scanning the sky every 3 nights, tracking anything that moves, changes in brightness. It'll pin it down and hand it off to scientists. And it'll be the machine that will find all the objects out in the Kuiper Belt that have the potential for New Horizons to visit. So it's unlikely that we'll hear of a new target for New Horizons in the next, before Vera Rubin comes online and starts gathering its data. But once it does, then I feel like it's almost inevitable that it will find a suitable target for New Horizons to visit next. And it should still have enough power. Its transmitters work. The spacecraft's doing great. But it is still doing science out there in the interstellar void. It is still interacting with particles from the sun, the heliosphere, the heliopause. It's going to be able to provide another perspective, another data point on what it's like in the outer solar system. It's also receiving cosmic rays. It's being hit by other particles from interstellar space. And it's able to actually get a very clear view of the universe outside of the dust in the inner solar system. And it's actually already been able to do some really interesting science in helping measure the amount of dust that is in the solar system compared to the rest of the universe. So I anticipate we're going to hear from New Horizons probably for decades. Hopefully when it goes by another target, but even if not that, it's going to be sending home science until finally its nuclear battery runs out of power and it goes quiet forever, like the Voyagers are about to do. J. James. Some scientists are saying that there is more universe, stars, and galaxies beyond what we can see and observe. How can the universe extend beyond what we can see when the cosmic microwave background is the beginning of time? Is the cosmic microwave background not the boundary of all matter by definition? No. The cosmic microwave background is not the boundary of all matter. It is purely the boundary of our observable universe. And the observable universe is in relation to the observer. Wherever you are, you can see out to light that has been traveling for 13.8 billion years, and that is your observable universe. But if you shift over a few billion light years, you will see a brand new observable universe. If you shifted 100 billion light years in one direction, you would see an observable universe that doesn't overlap our observable universe at all. And yet, in all directions, you would see the cosmic microwave background radiation. You would see galaxies that are brand new at the very distant reaches with your alien James Webb Space Telescope. And then you would see galaxies that are younger and closer, or newer and closer. And then you would see the most modern, mature galaxies that are all around you. And finally, you would see your own alien house. And so the cosmic microwave background is just your perspective. But the thing that I find really mind-blowing, the thing that I really love about this, is that when you think about the cosmic microwave background, it is this time in the early universe when light could finally escape. And it's not like it was like this birth cry of the universe. It was like this gradual transition from the entire universe kind of being like a star to the entire universe being transparent and light being able to move through it. But every second that goes by, every minute that goes by, every 1,000 years that goes by, a new region in a widening sphere around you is releasing that cosmic microwave background radiation. Or I guess had already released it, and now it is arriving at your detectors. And it's just getting bigger and bigger and bigger. And so every moment that goes by, you are detecting a brand new point of the universe. Now, it all looks roughly the same, and especially at the largest scales, it doesn't change within our lifetime. But if you could watch the cosmic microwave background over billions of years, you would see it shift and change in temperatures as this sphere of observability is expanding outward, and you're seeing new parts of the universe go to that point where it's releasing its light. So I'm going to give you an analogy. So think about a rainbow. Now, when you are outside and it's raining and the sun is down low on the horizon on the opposite side, you can see a rainbow. Now, isn't it weird that the rainbow is positioned exactly on the other side of you and the sun, right? Every rainbow is custom. The rainbow that you see is very different from the rainbow that I might see, even if we were standing very close to each other. And it's because you've got these droplets of water. The light from the sun is going through the droplets of water. It is bouncing back out the back. It's getting broken up, and it's arriving at your eyeballs. And it's individual water molecules that are shifting the light towards your eyes. But even if someone's standing just right beside you, they're seeing completely different water molecules that you aren't seeing, and yet together you both see a rainbow. And so no matter where you are, you see the cosmic microwave background, even though you're seeing a different cosmic microwave background. Dalton, I wonder how long it will be until we have a picture of an exoplanet that isn't just a light blob. A few years ago, I would have said 2060, but now I think it could be closer to 2030. I think one of the big disappointments that people had when James Webb came online is that we didn't get these incredible high-resolution images of planets orbiting around other stars. So we could see their mountains and their oceans, their forests and their clouds and stuff. We just get a dot. Just like we've gotten dots with other telescopes. And the reality is that James Webb isn't big enough to be able to resolve anything other than a dot. You'll get one pixel, one very interesting pixel, a pixel that tells you the atmospheric composition of the planet, a pixel that theoretically could, over time, help you map out the locations of continents and oceans and cloud cover and such. But really, it's just one pixel. And you could build a telescope that is 100 times bigger than James Webb, and you would still get a pixel. The only technology that has ever been proposed that would give us anything other than a single pixel is the Solar Gravitational Lens telescope. And this is where you send a telescope out to about 1,000 astronomical units away from the sun, where the gravity of the sun forms a natural lens. And now you're using the gravity of the sun as your telescope. And I've done an interview with Dr. Slava Turashev about the Solar Gravitational Lens. You would need a telescope that is 10,000 kilometers across to match the power of the Solar Gravitational Lens. And then you get to see a megapixel image of an exoplanet. So until we're building telescopes in the kilometer scale, the tens of kilometer scales, we're not going to get any kind of resolution that is better than one single pixel. And so like just prepare yourself emotionally for a lot of artist illustrations of planets, because it's going to be a long time before we're actually able to take a look and see a picture of a planet. But boy, once we get that solar gravitational lens telescope going, then you can imagine much bigger telescopes. Imagine a telescope that is tens of kilometers across, perched at the solar gravitational lens. Now we're talking. And so your time frame, you said a few years ago you would have thought 2060. Now you think it'd be closer to 2030. Both 2060 sounds more feasible to me. The journey out to the solar gravitational lens is about 20 years to get there. The construction of it is going to take probably 5 years. We're looking at 2050, 2060. That time frame feels about right. Helga Kwarting. Could life be possible around brown dwarfs, or are they not bright hot enough? A brown dwarf, also known as a failed star, is a star that has a mass that is a fraction of the mass for the sun. Like you're looking at a few percent. Like a red dwarf star, which is the lowest mass star that you can have to have fusion going on in its core, is like 15% of the mass of the sun. And so below 15% the mass of the sun, you've got a brown dwarf star. And it's still made of hydrogen and helium, but it's using a kind of fusion in its core that's different. So instead of it doing hydrogen into helium, it's fusing deuterium, a version of hydrogen. And they don't put out as much temperature, and they don't ignite like stars. They're very hard to find because they're very dim. You find them in the infrared with like James Webb. But could you have life around a brown dwarf? Sure. You can have life wherever you're going to have a habitable zone. And a brown dwarf star is still going to give off radiation. It's just not going to give off a lot of radiation. So you're going to have a planet that is curled up really close and tight to the brown dwarf. So you're going to have a habitable zone that is just a few percent. Like the planet is going to be snugged up really close to the brown dwarf. It's most likely going to be tidally locked, the same issues that we get with red dwarf stars. And the brown dwarf, isn't fusing hydrogen into helium. It's just fusing this deuterium. And when that runs out, it's going to stop putting out its heat. So it's not the best place to set up shop for the long term. But yeah, in theory, you could have a habitable zone. The idea that you need a sun-like star with a planet in the habitable zone is really getting overturned by the scientific community. People are finding that liquid water can be maintained in all kinds of circumstances. Like if you took the Earth and you just pushed it out into the universe away from the sun, there would be liquid water still inside our planet for billions, maybe even trillions of years as the planet cooled down, as the radioactive materials decayed inside the planet. You could have a brown dwarf with an ice moon around or an ice planet around it, and the tidal forces of multiple ice planets are interacting with each other, and you're getting like Europas and Enceladises around these brown dwarfs. So our idea of what is a habitable planet and a not habitable planet is really shifting and changing at this point. In Prado we trust. When will the SpaceX orbital test happen in your best guesstimate? So today we saw a test fire of the Super Heavy with 7 of its Raptor 2 engines. Before we saw 3, and then before that we saw 1, and we also saw an explosion of 1. So now we're up to 7, but there are 33 engines on the Super Heavy. So they're going to do some more static fire tests, building up the number of engines that they do. And if there's any problems, that booster could explode. So let's assume that they keep ramping up the tests over the course of a couple of months. I would anticipate seeing an orbital test of Super Heavy, and this is just like me picking a number out of the air, right? I'm sort of like I'm calculating all the variables. I've got I've got like, what is the amount of time it's taken to build Super Heavy so far? What is the Musk time multiplier? How technically complicated is it to continue development of this rocket? Starship is complete. Super Heavy needs to be tested some more. Are they really not going to do a test flight of Super Heavy? They must do a hop test with Super Heavy. So I would suspect we would see that before we see an orbital flight. March. That's my guess. March. That we should see a orbital flight of Starship in March. But that is a guess. I have very little to go on beyond my experience at this point. Constellation Pegasus. What are your thoughts on finding gravitational waves in the cosmic microwave background? When the Big Bang began, we've got this rapid expansion of material in the universe, and it wasn't even, and so you got gravitational waves rippling out from all the places that this happened. Like, you create gravitational waves as you're just walking around, and if you've got enormous amounts of mass, like chunks of the universe amounts of mass moving around, you're going to get gravitational waves. And those gravitational waves are going to have a very long baseline. They're going to take a long time for those gravitational waves to pass the Earth. And yet, just with the cosmic microwave background that we talked about earlier, as time goes on, we will see the gravitational waves from the beginning of the universe at different regions, at this expanding outward sphere of the beginning of the universe generating its gravitational waves. And so it's never too late to tune into the gravitational waves at the beginning of the universe. The instrument that it would take to actually be able to see those gravitational waves is probably the space telescope that's going to come after the LISA Space Observatory. So LISA, the Laser Interferometer Space Antenna, which is the European Space Agency's space-based gravitational wave observatory, that's due for launch in 2035. We saw the precursor of that, like a test mission, demonstrate that the technology is there. But in 2035, we will actually see this 3 spacecraft constellation be flying in space, and is detecting gravitational waves. And it will be much more sensitive than the ground-based gravitational wave sensors that we have here today with LIGO and Virgo and Kagra, etc. And LISA should be able to detect the mergers from supermassive black holes. Right now, we can only detect the mergers of regular black holes, stellar mass black holes, but now we'll start to be able to detect the ones with the longer baselines. But even LISA won't be able to detect those gravitational waves coming from the beginning of the universe. That's going to take a more sensitive instrument. And the name for that is called the Big Bang Explorer. It's essentially LISA, but instead of 3 spacecraft firing in formation, you've got 12 spacecraft flying in formation. And then together, they are generating this gravitational wave net that is able to detect the background hum of the gravitational waves of the universe, essentially the gravitational waves that came from the origin of the universe itself. And when astronomers can actually see that, it will be a revolutionary observation that they're able to make. It will confirm or deny many theories about the Big Bang, because now they're actually watching the Big Bang unfold. The big problem with the cosmic microwave background radiation is that this is light that was released about 380,000 years after the Big Bang. Before that, the universe was opaque. We can't observe it. We can't use telescopes to observe it. But it's not opaque to gravitational waves. Those gravitational waves were released right at the beginning of the universe. And so the key to seeing earlier, to confirming the theories about the Big Bang, is to be able to see the universe in those gravitational waves. And you need to have that really sensitive instrument. And that's going to be the one, the Big Bang Explorer, Big Bang Observer. But like, it'll be the telescope that comes after LISA, which isn't due for launch in 2035. So like 2045, we should see the Big Bang Observer fly, or like more spacecraft join LISA to be able to make those images. More questions in a second, but first I'd like to thank our patrons: Kenneth Watman, Ralph Husky, Mark Biddick, Don Archangel, Christopher Pavlicek, Ian Whitford, Daniel LaBelle, Kevin Woods, Ekartina Shudoskaya, Madeline Williams, and the rest of our 1,049 patrons for their generous support. Want our videos with no ads? Join our community at patreon.com/Universe Today and also remove all the ads from Universe Today for life. John Brown, if the universe expanding collides with another universe, how would we know? We wouldn't know until we couldn't know anything. But one idea of string theory is this idea that the Big Bang was formed by these membranes that bumped into each other and set off this new version of the universe. Another possibility is this idea of continuous inflation. Like the very theory of inflation, the very beginning of the universe went through this really rapid rate of expansion, has actually been continuing on at different parts across the multiverse, across all of the universes. These universes are forming nonstop in places where inflation has never ended. And so I guess in theory, you could have universes, if they are finite, then the universes could be overlapping one another. And you would have this place where I don't know, it's like a Venn diagram of universe where you've got the laws of physics from one universe overlapping the laws of physics from the other universe. What would happen in the middle? Well, you would have the laws of physics making no sense to either universe, which would be bad for life and everything. It's been theorized that some weird anomalies in the cosmic microwave background radiation could be explained by universes overlapping into our universe. How would you know that something's happening? Well, nothing can go faster than the speed of light. And so as the universes are colliding with each other and the implications of those collisions are rippling out, they would be rippling out at the speed of light. And that's also the speed at which you could observe them. And so you'd be there sitting, looking at the universe, and it looked absolutely normal. And then suddenly the wave of confusion passes over the Earth, and now the law of gravity doesn't make any sense. The molecular cohesion doesn't make any sense. You come apart at an atomic level, and all of your fields dissipate into the universe or turn into unicorn tears. So you wouldn't know. It would have just happened, and suddenly you would be in non-existence. Helga Quarting. With Titan slowly moving away from Saturn, will it eventually be ejected from the solar system, or would it make a mess in the surroundings? How would its moving away affect other moons? Titan, well, many of the moons in the solar system are moving away from their planet. The Earth's moon is moving away from the Earth at about 4 centimeters a year. And it looks like Titan is moving away from Saturn at about 11 centimeters a year. And that was actually surprisingly quick. There's fairly new research that found that, in fact, Titan is making a very dramatic change in its distance. But I say dramatic, but like 11 centimeters is still not a lot. Like the moon will take tens of billions of years before it completely drifts away from the Earth and is captured by the sun. And so Titan would be the same thing. And of course, the big time limit on the solar system is the death of the sun. The sun will die in 5 to 6 billion years from now and gobble up the inner planets and mess up the orbits of the outer planets. And if Titan is still drifting away at that point, I'd be amazed. The other thing that is sort of working to the dissolution of the Saturn system is the interactions with Jupiter. And one by one, the planets are going to get kicked out of the solar system by the gravitational interactions of Jupiter and Saturn and the other ice giants. And within about 100 billion years, all of the planets will probably have been kicked out of the solar system, even though the sun is long dead and is just a white dwarf star. And also interactions with other stars that are coming too close to our solar system. So I wouldn't worry about Titan making a mess with its surroundings. I wouldn't worry about it disappearing from Saturn. Space is big. 11 centimeters is not very quick, and can travel out for longer than the solar system will be around. Gonzalo Lozada, do you think that antimatter black holes could exist? What would happen if it collides with a regular black hole? This is a question I've done a whole video on, and we covered this in Astronomy Cast, and it's interesting this question keeps coming up. So there is no such thing as an antimatter black hole. There are just black holes, and black holes are made of black hole. They're not made of matter, they're not made of antimatter. And so follow this thought experiment. If you take the Earth and you feed it to a black hole, you've got a black hole that now has the mass of the Earth. But if you take an Earth's worth of energy and you feed it to a black hole, maybe in the form of light, you will get a black hole with the mass of the Earth, because through E equals mc squared. So you've got the E, which is the energy that you're putting in, is going to be equal to the mass of the Earth times the speed of light squared. So it's an enormous amount of energy. And yet if you fed that to a black hole, you would get a black hole with the mass of the Earth. And you wouldn't know which one it was. Was it a black hole made of energy or a black hole made of mass? So when you put matter and antimatter together, what you get is energy. And that can turn into a black hole just fine. And so if you had a black hole's worth of matter and a black hole's worth of antimatter and you mash them together, you would get two black holes worth of energy via E equals mc squared would be twice the mass of the black hole. So it just doesn't matter. Matter, antimatter, energy, it all just makes more black hole. And so if you put mashed a matter black hole with an antimatter black hole, you ended up with a black hole with twice the mass. You wouldn't get that annihilation, that sweet, sweet annihilation that you were hoping for. This is not the way to get rid of black holes. Jason Cullen. Hey, Fraser, with the technology that we have, what is the farthest we can fly into Jupiter or any of the other gas giants? Not far. A couple of 100 kilometers under the top of the atmosphere would destroy any spacecraft that we would try to send. And we've actually done this. When the Galileo spacecraft arrived at Jupiter, it released a probe that descended into the cloud tops and detected the atmosphere of Jupiter as it fell. And then it got crushed by the intense pressure and temperature inside Jupiter. When the Galileo spacecraft reached the end of its mission, it was crashed into Jupiter and didn't get very far. When Cassini ended, it was crashed into Saturn and it didn't get very far. And the reason is because when you imagine a gas giant, I'm sure you're imagining this great big fluffy cloud, this puff ball of gas that's just out there floating in space. But it is not. It is hundreds of thousands of times the mass of the Earth mashed together under mutual gravity to the point that the density at the core of Jupiter is starting to approach what it would take to ignite fusion, or at least deuterium fusion. It's very hot. And we talked about this story, how it rains diamonds on Neptune and Uranus because you've got carbon atoms that are getting mashed together by the pressure and temperature inside the upper atmosphere, the upper layers of Neptune, into diamonds. And then they are raining down inside the planet, and then they're being dismantled at an atomic level by the heat and energy inside Neptune. And then this stuff is floating higher up again, and they're being mashed into diamonds again. Like at the core of Jupiter, hydrogen, the lightest substance in the universe, is turned into a metal. Like it's more dense than anything that we can fabricate here on Earth. It's ludicrously dense. So a couple of 100 kilometers, and then you start to hit higher and higher densities, and anything that we could build would be crushed. Ruling Moss 55. Do planets like gas giants have an expected lifespan like stars, or will they outlive all stars in the universe? Stars have a lifespan because they are consuming material in their core. When you've got a star like our sun, it is turning hydrogen into helium at the core. When it runs out of hydrogen and helium, it'll puff out as a red giant. It'll blast out its outer layers, and then it'll turn into a white dwarf and cool down to the background temperature of the universe. But did it die? Or is it still just a block of carbon out there, the largest diamond in the universe? A planet like Jupiter, if it had no star, it would continue to radiate heat from its creation, from its formation. Then slowly over time, it would cool down and cool down and cool down. And then it would just be this blob of dense hydrogen and helium floating around in the universe, cooled down to the background temperature of the universe. Is that alive? Is that dead? So, when we think of things being living, it's things like stars that are undergoing some kind of process in their heart. But we know that the future of the universe is the heat death. And so trillions of years from now, all of the gas giants will be cooled down to the background temperature of the universe. And they'll just be these blobs of hydrogen and helium floating around. Although I say blob, but of course, incredibly dense blobs of hydrogen and helium. And it'd be cool. I mean, you could imagine some far, far future, enough of those Jupiters merge together that a star could ignite again. And you'd have these moments of ignition of stars, because it is fuel for new stars. And so I guess as long as there's still fuel out there, there's hope. And I guess they're little nuggets of fuel for future stars. But like when you think about like deep time, like it's really hard. Like everything is going to be in a black hole or has escaped a black hole. And it'll be those planets floating around that just had never ended up in a black hole. That I guess the hope for a bleak universe future. Joseph W.M. Is there an edge to the universe, and is there a multiverse and beyond? There might be an edge to the universe. It just depends on whether the universe is infinite or finite. If the universe is infinite, then no, there is no edge to the universe. If the universe is finite, there still isn't an edge to the universe, because you would essentially you'd return to your starting point. So if you were flying out in the universe in one direction, if the universe was finite, you would just return to your starting point. Kind of in the same way that if you drive on the Earth, you return to your starting point if you drive in one direction long enough. The surface area of the Earth is finite. Is there a multiverse? We have no idea. We may never know if there are other universes out there. There are theories that try to explain how quantum mechanics can get weird, and that could be in a multiverse. And there are versions of multiverses that you can find in an infinite universe that don't require getting weird with quantum mechanics, but we really have no idea if there is multiverses or beyond. Christopher Bergen, when will the cosmic microwave background no longer be detectable, and will some part of the electromagnetic spectrum be redshifted to the new CMB? The cosmic microwave background today is in microwaves. You got to observe it in microwaves, but it wasn't always. When the cosmic microwave background radiation was released, it was like the temperature of a red giant star. So it was like 3,500 Kelvin, and now it's cooled down to about 3 Kelvin. And that is not that the light has cooled down. It is that the expansion of the universe has redshifted the photons to the point that they are now shifted into the microwave. And that redshifting is just going to continue on over time. It'll shift into the radio waves, and then into longer and longer radio waves. And there will come a time when the cosmic microwave background is no longer detectable by microwaves. It'll be shifted into the radio waves. And in a trillion years, maybe, you would have a hard time detecting that CMB was even there at all. But it'll always be detectable. And as long as our technology continues to advance, or future astronomers continue to advance, they will build bigger and bigger radio telescopes capable of detecting bigger and bigger signals from the cosmic microwave background. So it'll always be there. It'll just be harder and harder to find. It'll be discovered later in the technological development of the species. Francis Morin, do we know what will be used to block cosmic radiation on the Lunar Gateway? Nothing. The Lunar Gateway is this space station that's going to be positioned out near the moon. It's going to be on this orbit that brings it closer to the moon and farther from the moon, and it'll serve as this way station where the astronauts will fly from the Earth, stay at the Lunar Gateway, and then they'll transfer down to the surface of the moon, and then back up to the Gateway, and then back down to the Earth. And they are outside of the protective magnetosphere that the Earth provides for the folks on the International Space Station. And so they're going to get a full dose of the cosmic radiation. And it is hundreds of times worse than being protected by the Earth's atmosphere and magnetosphere. And so astronauts will receive a lifetime dose of radiation by spending just a few months out there on the space station. Like, chances are astronauts that go back to the moon, that'll be their only trip to space. They won't get to do a lot of this. How will they be protected? So there's a few ways. So one is the walls of the gateway will be built a little thicker. The Orion capsule is going to have some radiation protection built inside, but the plan is to build a fort. If there's like a solar storm that's incoming to the Orion capsule, the astronauts will take everything that they have, pile it up in this defensive manner, go to the best shielded part of the capsule and ride out the storm. And they'll do something similar when they're on board the Lunar Gateway. So you'll have this mix of stuff, your water, your wastewater, your food, your supplies, all of that you'll hole up in the middle of as much protons as you can on board the station to protect you. But for the rest of the time, you're just going to be out and about doing your thing. You're going to be getting hit by cosmic rays from space, and that is just the price that the astronauts have got to be willing to pay to go to space. Would you fly to the moon if you knew that it would give you a vastly higher chance of getting cancer in your lifetime? Would you regret doing it after you get the cancer? I don't know. These are tricky problems. We don't have good radiation shielding. Now, we have ideas for how to do it. Lots of water is great, but lead, any kind of heavy amounts of protons would do the trick. And so do we wait to go to the moon until we've got really good radiation shielding built up, or do we just go to the moon? Once you get to the moon, you can dig under the regolith and hide out against the radiation, or you can go and set up at the bottom of a crater where you're only receiving a fraction of the radiation. If you read Seven Eves, they talk about how they set up a base on the moon at the bottom of a ravine. And so you're only getting just a tiny fraction of the radiation that is coming in from directly overhead. The rest of the time, you're protected by the moon. And so that might be the way to go. But yeah, there are no real plans to protect astronauts significantly against the radiation of space. It's just the occupational hazard of being an astronaut. All right. Those are all the questions that we had this week. Thank you, everyone, for joining me, both asking questions in the YouTube comments, but also joining during the live show, which we record every Monday at 5 p.m. Pacific time. There should be an event for the next one here on the channel somewhere. So click to be notified of that event when we go live, and come and join and hang out. All right, we'll see you next week. You can get even more space news in my weekly email newsletter. I send it out every Friday to more than 55,000 people. I write every word. There's no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and questions and answers, as well as exclusive content. Subscribe at universetoday.com/podcast, or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Josh Schultz and Andrew M. Gross, who supports us at the Master of the Universe level. All your support means the universe to us.